What's up, everyone? Today we're talking about the aerodynamic interference between aircraft elements. So an aircraft is usually consists of more than one element, and the aerodynamic effect of each one usually interacts with each other. And that's why usually aircraft are usually optimized for working together. So to look at this, we're going to look at this paper called Measurements of Aerodynamic Interference of a Hybrid Aircraft with Multi-Rotor Propulsion. And in this paper, they look at one particular aircraft. It's a autogyro, or it's called a gyroplane. And these are effectively like helicopters with rotors on the back. So they were very popular back in the early 1900s. But then since then, the helicopter took over in popularity. And in the 1940s to 1980s and even later, that became far more popular. And now the autogyro is making a bit of a resurgence. So they go on in this article and say that it deals with the phenomenon of aerodynamic interference occurring in the innovative hybrid system of multi-rotor aircraft propulsion. And the reason why multi-rotor aircraft are interesting is because obviously multi-rotor means it has more than one rotor, which means that you have more than one area on an aircraft producing thrust or even lift, depending where the rotor is and how it's positioned. So there's a lot of downwash and wake that's hitting other parts of the aircraft, and that can create a lot more interference. And what's more, depending on the conditions that you're traveling at, the velocity of the air and the rotor speed, etc., these can change. So the approach to aerodynamics requires a determination of the impact of active sources of lift and thrust upon the aircraft aerodynamic characteristics. The hybrid propulsion unit, composed of a conventional multi-rotor source of thrust as well as lift in the form of the main rotor and a pusher, was equipped with an additional propeller drive unit. So, as I just mentioned before, a helicopter is similar, except it only has one rotor producing lift and thrust. Then you have the tail, which is more for the stability, so it doesn't keep rotating around the axis that the main rotor is rotating around. But with an autogyro, you have one rotor, as you would with a helicopter. Then you have one rotor which is pushing the aircraft along. So it's usually at the back, and its axis of rotation is the direction of travel, effectively. So the rotor on top produces the lift, and the rotor at the back produces the thrust. That's how it differs to a helicopter. So they did some force testing, and it made it possible to develop aerodynamic characteristics as well as defining aerodynamic characteristics and defining the field of speed for the considered design configurations. An introduction to the gyroplane. It is a type of rotorcraft that was originally developed in Spain in the 1920s. The first successful flight of the Sierva C4 rotorcraft took place on the 9th of January 1923. According to the authors of the fifth reference in this paper, which you can look at the paper if you like, the emergence of gyroplanes and the conducted investigations in the 1920s and 1930s paved the way for the development of helicopters in the 1940s. A number of technical in-flight problems led to rotary wings, especially in relation to the solution proposed by Juan de la Sierva, were noticed at the time. For example, the gimbal mount of the main rotor blades, and that was also a problem for helicopters as well, but they managed to solve that. They have different buckle systems, and that's not important though for what we're looking at today. As helicopters became more popular than autogyros, the latter were affected by the so-called dead period, mainly because of the wars, politics, and history, but not due to technical issues of the machines. In recent years, however, there has been a revival of interest in the type of flying machine, both as an entertainment aircraft as well as a cheap alternative to helicopters. So after conducting simulation tests, one group found that the overall characteristics of gyroplane stability are a combination of flight models for a helicopter and an airplane. So that's something interesting to note as well. So because you have this configuration where you have one rotor producing lift and one rotor producing the thrust, it's kind of a cross between helicopters and airplanes, but also the stability and the flight dynamics also between those two ends. That means that the aerodynamic interference that you get not only affects just the general lift and drag as we look at it, but also the pitching moment, the roll, the yaw, and etc. So The results of another analysis showed a significant effect on the fuselage on the aerodynamic properties of an aircraft. It turned out that the unfavorable limitation of progressive speed largely depends on the autorotation performance of the rotor. So with this, let's talk about this for a little bit. So the fuselage in any aircraft is usually the main part that everything else is built around. And that's usually what carries the payload or the humans or whatever. And in airplanes, there's been a lot of research into how to make a fuselage work well with the wings. So for example, you have something called the Whitcomb Law. And the Whitcomb Law states that in an aircraft, in a plane, particularly if you're traveling very fast, you shouldn't have such a big change in the frontal area as you go down the aircraft. So if you take cross sections of the aircraft, the frontal area of that cross section should always be fairly similar to the cross section before, upstream and downstream. If you have all of a sudden big changes, you can get shocks forming and wave drag increases. So what they do with the fuselage in the airplane is that when it comes to the wings, because the wings then produce a lot more surface area, when you take cross section, they then taper the fuselage in a little bit. And you can see that on any aircraft, on any airplane you go on. If you look at around the wings, you'll see the fuselage is sort of pinched a little bit in the middle. For the autogyro and the helicopter, you have the wash of the main rotor, the above, impinging straight onto the fuselage. So now you have a different type of flow impacting the rest of the aircraft, and that's going to be affecting the aerodynamic properties. And in this particular case, they said that it turned out the unfavorable limitation of progressive speed largely depends on the autorotation performance of a rotor. So let's discuss this for a little bit, because this is an interesting point. So the progressive speed largely depends on the autorotation performance of a rotor. First of all, what is the autorotation performance of a rotor? The autorotation performance is effectively the glide aspect of a helicopter or autogyro. So with an airplane, for example, a glide is, we all know what glide looks like. You just let the engines idle and then, or maybe power them down a little bit, and then you're now descending and you're using the potential energy that you have to keep going a little bit forward. You still generate a little bit of lift. So for a rotating wing aircraft like a helicopter or autogyro, what happens is you power down the engine as well. So that means that the rotor that's producing lift or even thrust is no longer producing that much of the thrust, not imparting energy onto the flow. You're actually using the energy of the flow to continue to maintain lift. So the limit of how fast you can go is dependent on that. And with helicopters, you can often see this when a helicopter enters this maneuvering aspect, because the rotor then tilts a little bit flatter. So when you look at a helicopter going forward, the rotor is tilted down a little bit and the entire helicopter is tilted down as well a little bit. And then as it goes into this auto rotation mode, it sort of straightens up and becomes a little bit more level, including the rotor. Okay, so moving on with this paper, one of the desirable characteristics of the gyro plane is the performance of a vertical takeoff and even a hover, which is why rotating wing aircraft are so desirable. Another important criterion is achieving high cruise speeds which do not interfere with the limitations of noise emissions from the main rotor. An implementation of the above assumptions makes it possible to build a rotorcraft whose capability will exceed other helicopters as well as being competitive to aircraft. So I just want to talk about the part where they said achieving high cruise speeds, but do not interfere with the limitations of noise emissions from the main rotor. So why is that? Well, let's look at the helicopter to begin with. So a helicopter uses this main rotor, and it really has one rotor for lift and thrust to do that. So it's working incredibly hard to produce both of those forces. Obviously, you only have one force, but it decomposes into those two directions. And so you're relying on this one rotor to do all this work. And that means you need to spin the rotor very fast. Now, as you travel forwards, the helicopter itself will have a certain velocity. So let's say it has 100 meters per second forward velocity. Now, as the rotor is traveling around, it's going in a circle around the top. So the blades moving forward are not only moving at 100 meters per second, they're also moving with the velocity of that rotation forward. So if it's rotating at, let's say, another, it works out to be another 100 meters per second forward, at one point, it'll be 200 meters per second forward. And then as the blades are traveling the opposite direction around the other side, they will be actually traveling at 0 meters per second relative to the ground, or relative to the free stream velocity of the still air. So that means that you can only push the aircraft to a certain velocity before shockwaves start forming on the helicopter blades, what's called the critical Mach number. And with those come increased noise. So if you work a rotor more, so you push it at a higher angular velocity, it's going to be reaching this limiting case much earlier in your flight. Contrasting that with a auto gyro where you have two rotors now one producing the lift and one producing the thrust. That means that these rotors are not having to work as hard because one rotor is doing one job, the other rotor is doing another job. So you don't have to push these rotors to go as quickly around, which means that you can travel at higher speeds forward before hitting this critical Mach number, and also producing so much noise to being not allowed. So that's why auto gyros can then start approaching airplane speeds, going faster than helicopter speeds, because it can get around that problem that helicopters always run into. So moving on, they just note as well that the rotor generates thrust by accelerating the air that flows through it. So that's fairly obvious. You use Newton's laws to produce a force in the opposite direction. And then they go on and they say in helicopters, the auto-rotation maneuver is used to land in the event of a loss of engine power. During this maneuver, the collected input data are used to control the airspeed while reducing the altitude and exploiting the energy stored in the main rotor. Apart from the strategy of auto-rotation, landing directly piloted, several automatic strategies have been developed. The majority of them contain a simple system of flight control using the concepts of simplified aircraft dynamics so as to land in a predefined area. And then they go on and say that the phenomenon of aerodynamic interference, as defined in Werq 33, so the 33rd reference in this paper, as a mutual interaction of flow of aircraft elements arising from the fact that they are produced by load-bearing elements of flow disruption, also deformed by non-load-bearing elements, e.g. fuselages. They mutually distort the generators of force, thus affecting back the flow fields generated by them. So what this is saying is that it's not just the parts of the aircraft that produce force, so they're doing the work. They're also the passive parts of the aircraft as well that have this feedback where, with a helicopter, you have all this air being forced down. A lot of that's going to be hitting the fuselage. So the fuselage is now creating this blockage, which is going to affect the upstream flow, which is the rotor and going through the rotor. So there's this synergistic effect, but in a negative way. In Werq 39, so the 39th reference in this paper, this phenomenon was defined as a phenomenon of mutual interaction of various parts of the aircraft. So as we mentioned, that all these different parts are working together or against each other, depending how well you design the aircraft, as a result of which the aerodynamic force influencing the whole aircraft is not equal to a sum of aerodynamic forces affecting its isolated components, such as the wing, fuselage, stabilizer, and so on. So if you were to test each one of these components, so the wings, the fuselage, the horizontal stabilizer, the vertical stabilizer, etc., and you look at not only the drag, but also the lift and the side force and whatever you want, and then you tally them up, that will not equal what the entire aircraft is experiencing, because these do affect each other, the aerodynamic performance. It is very important to properly shape the geometry of an aircraft. Special attention needs to be drawn onto the place of joining the components, e.g. wings with a fuselage. So that was actually a reference to what I mentioned earlier, the Whitcomb Law. I don't go through it here, but it's you can look it up very easily. A proper connection of the components allows for reducing interference drag. In special cases, the aerodynamic drag of an entire aircraft can be smaller than the sum of aerodynamic drag of its isolated parts. That is true in some cases, but in other cases it isn't. It really depends on how you've designed the aircraft. So in this paper, they looked at a really cool aircraft. They have effectively a helicopter. So the fuselage itself is tapered in like the egg-shaped sort of thing. Then you have the familiar helicopter rotor. The back has a typical airplane tail. So this is actually a boom tail. So it has two things going back, and then you have the horizontal stabilizer above two vertical stabilizers. And then in addition to those, you have the pusher rotor, which is at the back pushing the aircraft forward. And you have 4 additional rotors producing lift, one on each corner of the aircraft. And so you have the front left, the front right, the back left, and the back right. So in total, there's actually 6 rotors on this aircraft, 5 of them are producing lift to some extent. One of them is producing the thrust. And they 3D printed this model and they tested it in their wind tunnel. So the maximum speed of the air in the tunnel was 40 meters per second. And the minimum was 10 meters per second. And the turbulence density was 0.5%. They limited it to that. Now, is a turbulence density of 0.5% accurate in real life? It depends on the conditions. So depending where you are, if you're very close to the ground, probably not. Like today, actually, now that I'm talking, there's very windy. So the turbulence density would probably be like 30% right now. But if you go very high up, then you will drop down to 0.5% or even lower, depending on how high you go. So depending on where you are in the flight envelope, you will be potentially looking at that turbulence density. And they looked at different forces. So they looked at the drag force, the lateral force, the side force, the lift force, as well as the rolling moment, the pitching moment, and the yaw moment. The configuration was tested with an air blast equal to 12.5 meters per second in order to determine the aerodynamic forces influencing the aircraft and the examination of the impact of the angle of attack on the generated forces. The engines were started up at 50%, and they also went to 100% as well later on. And they also tested this aircraft ranging from angles of attack from 0 degrees to minus 13.5 degrees. So these blades were rotated at different angles of attack. And they tested them with all these forces, and what they found, so theoretically, without any interruptions or a mutual impact, the combination of these 2 systems should ensure a summative thrust force, in the first case equal to 30.83 newtons for power equal to 50%, and in the second one, 46.93 for a power equal to 100%. So first of all, this is theoretical. Secondly, it's interesting to note that this usually happens where you have a power of 50% and the thrust is 31 newtons about. You then double the power to 100%, but the force does not go up twice as much, it only goes to 46.93 newtons. So it's like, what's that, about 52% higher, whatever it is, or maybe a bit higher. So there's non-linear effect. In addition to this, they then looked at the actual results that they got. So theoretically, they should have gotten these 2 thrust performances. But due to aerodynamic interference, so the aerodynamic interference between all these different rotors and the fuselage, etc., and in these values are equal to 28.02 newtons and 38.98 newtons, respectively, which is a reduction in the value of the lift force with reference to the theoretical value, resulting from a sum of forces generated by the system, with each force considered separately. So compared to the theoretical values, there was a reduction of 9.1% and 16.9% respectively at 50% and 100% power in real life. So that's how much these systems all affected each other. So they go on and say that these are extreme values. However, in conditions of a proper operation of an aircraft, they become reduced because of a smaller demand for lift force. Assuming that the gravity force of an unmanned aerial vehicle is equal to the force generated by the main rotor carrier, so in other words, in just steady flight, steady level flight, it is definitely possible to reduce the need for power of a multi-rotor propulsion unit operating in a horizontal plane. Thus, reducing a negative impact of aerodynamic interference is anticipated. So in other words, this is the worst case scenario. In regular flight, these values would not be as poor. However, one thing that they didn't touch upon in this paper is, and I talked about it just briefly here and there, is how an aircraft is designed. So you can design an aircraft that all the components together work to give a much better result, so lower drag and higher lift than just each of its parts summed up together, so greater than the sum of its parts. However, this is fairly difficult for helicopters, and the more complex aircraft you get to, the harder it is. So an auto gyro, for example, with this particular case, 6 rotors, that means you then have 6 different sources of force, and then you have the fuselage and the tail. So that's now having so many different parts you need to work together, design together to make it work even better. What's more, it depends on your operating conditions. So if you're accelerating, if you're decelerating, if you're increasing your altitude, reducing your altitude, if you're going to the auto rotation mode, depending on which mode you're in, which part of the flight envelope you're in, the aircraft will not be operating in the same synergistic fashion. So you might optimize the aircraft to go in cruise, which is usually what you do for airplanes. But as soon as you go to taking off, if it's vertical takeoff, if it's a short takeoff, whatever, or landing, you're not going to have nearly as much synergistic effect as if you were in the cruise phase, because you haven't designed it for that. So that brings us to the end of this podcast. Make sure to check out the experimental instrumentation that we make here at Aerodynamics. It's really good. It makes all your experiments way better. Check out the courses that we do to make you a better aerodynamicist, and check out the International Aerodynamic Conference. This conference we put on every year for aerodynamicists. So peace out.